Hello, in this video we will talk about the laws of motion, and for the first time we will deal with why things move. And according to one Isaac Newton, that's because there is something that he called a force, which is the ability to accelerate a body. Notice that it's the ability. It won't necessarily create motion. For instance, if you push on a big rock, it might not move. Or if you push on the wall, it might not move because there are other forces preventing that motion. Now, forces can be, the most basic way to classify forces will be either a push or a pull. If you push on your book downwards towards the table, it's not going to move. But if you pull, you might be able to lift it, which means the direction of this quantity is important, and that makes force a vector. Right. Another category, another way to classify forces are short range and long range. These are called contact forces, and long range are called field forces. Examples of long range or field forces will be gravity. That's a good example. The electromagnetic force is also a force that is able to do stuff at long ranges. When you touch your book, you lift your book, you're touching it, so that's a contact force. More generally speaking, cosmologists will tell you that these four forces, gravity, the electromagnetic force, something called the strong force, and something called the weak force, are responsible for everything that happens in this universe. Everything. Of course, gravity needs no introduction, and the electromagnetic force will be discussed further in another course. But I can tell you, for instance, the strong force is what allows protons to live together inside the nucleus of an atom, like helium. Protons repel each other electrically, as you well know from high school. So what keeps them together inside the nucleus? Well, that's the strong force. And about the weak force, well, the weak force is responsible for transformations that happen, well, inside protons and neutrons. Protons can become neutrons and neutrons can become protons because of the weak force. But then these two forces will be explained further in your course of waves on modern physics. Let me give you an example of why cosmologists say that these four forces can explain everything. Like the example I gave you before, this is your hand and this is the wall. When you push with your hand against the wall, what happens is the atoms in your hand and the atoms in the wall interact. You think you're touching the wall, you feel the wall, but in reality what you are feeling is the electric interactions between all the atoms in one hand and the atoms in the wall, repulsions and attractions, and that is what it means to touch something, to push on something, or even to pull. It's the electromagnetic force at play. As we said before, a force then is a vector, and as such we can always decompose a vector in its x components and its y components. And throughout the semester, we're going to be using this a lot, especially if we ever need to find the resultant of two forces by adding the vectors. Now let's imagine this experiment. You have a truck, and then the truck has somebody inside. So that somebody is on top of a fancy skateboard with super good wheels, so there is no friction. And at the beginning, the truck is at rest and everybody is at rest. Okay, and then you have somebody outside the truck on the floor, on the ground, with an X-ray camera. X-rays. So that means we can see through the walls of the container. The container in the truck has no windows. There is a light, so the person inside can see what's going on. Now, the truck, it's an electric truck, so there is almost no noise. So when the truck starts moving with an acceleration, what's going to happen? The person inside is going to feel as if the truck is moving. Right. No, sorry. The person inside is going to feel as if he is moving, right? As the truck moves to the right, right? What eventually will happen is that the truck, I'm going to put it here, down here, but it's the same. Right now, the truck is here. My goodness, what an ugly truck. The truck is here. Just has moved a little bit. But then the guy, you see, the guy is still at the same position. We see through our camera that he has not moved. It's the truck that moved at constant acceleration. The person inside, however, feels as if it's him, the one moving to the left or moving in this direction. Right. Well, the difference is that the truck represents a non-inertial frame of reference. We are out here with a camera, we are in the floor that is not moving. We live in an inertial frame of reference. The difference is that when you are in an inertial frame, the acceleration is 0. When you are in a non-inertial, the acceleration is something. You have acceleration here, you don't have acceleration. So one of the observations that Newton made was that in an inertial frame, so like here, if there is no force, then there is no acceleration. And this is the first law. First law of mechanics. My goodness. This is the first law of mechanics. The first law of motion. Newton's first law. In an inertial frame, I didn't write that. If there is no force, there is no acceleration. From our point of view outside with the X-ray and everything, we clearly see that nothing is acting on the skater, right? And that's why he stays put. From the reference point of the truck, the person seems to move, to accelerate towards the left without any force being applied to him. And the reason, so there's a ghost force, but that force doesn't exist. And what happens is that this statement by Newton does not apply to non-inertial frames of reference. It only applies to inertial frames. Because you see, here we seem to have acceleration without a force, and that goes against Newton's first law. The Earth has centripetal acceleration around the sun, so the Earth is non-inertial, but the acceleration is very small. We calculated that the other day. It's something to the -3 meters per square second. So it's very small, so we still assume the Earth is an inertial frame of reference. Notice that this statement tells us what happens in the absence of a force. It doesn't say anything yet about what happens if the total force is zero. And then, to better phrase Newton's first law, there is this, which is what the book gives us. In the absence of external forces and when viewed from an internal reference frame, an object at rest remains at rest and an object in motion continues in motion with a constant velocity. That means no acceleration. So basically what I said before, zero force means zero acceleration. Since the time of the ancient Greeks and the Aristotle and everything, the general idea was that the natural state of motion was rest. It makes sense. Drop something, it's going to fall on the floor and it's never going to move again. But then Galileo challenged this, saying, no, the natural state of motion is to resist a change, which then eventually Newton put in these words. Meaning, if you're not moving, you will stay like that unless a force is applied. Similarly, if the object is already moving with constant velocity, it will move forever at that velocity unless a force is applied to change it. That tendency to resist a change in motion, we call it inertia. And for that reason, the first law of Newton sometimes is called the law of inertia.